Okay, welcome everybody. I'm sorry for my voice. Well, it's a great pleasure to present Professor Svi Mazeh. I will try to give you a few data of him if I can. So, well, first thing, he did his PhD in the Tel Aviv University, and after a postdoc there, he moves for a postdoc to the Berkeley University, and later he returned to the Tel Aviv University, where he became an associate professor and much later a full professor. Now he's still there like a full professor. And well, he has been also director of the WISE Observatory and other institute there in the University of Tel Aviv. He has also received several prizes. Among them, I would like to mention the Weizmann Prize, that is an important prize in Israel. But also, he has been a very successful researcher, and in fact, he has obtained an ERC advanced grant of the European Union. And well, his major area of research is exoplanets, where he has been one of the pioneers. Especially, he has been one of the pioneers in the radial velocity techniques, so in the first searches for exoplanets with the radial velocity. And also, he has been pioneer in the development of method for searching for transit planets. And also, he has also a special interest in binaries, and especially in spectroscopic binaries, where he and his group have developed a very interesting tools to determine the orbit and separate the components of different spectroscopic binaries. And well, today, well, he's a Juan Serra grant of the IC, so he's visiting us for several months. And today, he's going to speak about the obliquity of exoplanets, so about the alignment between planets and the host and the spin of the host star. So, Steve, thank you very much.
I'm thankful to Hans and Raphael who are hosting me. So it has been a wonderful time, and I look at the calendar, and it's or the end of my stay is coming close. All right, so today my talk is a mixture of two subjects. One is some characteristics of the population of giant planets, maybe, and the other one is stellar rotation, and I would like to connect the two. So this is what I'll talk about, and I will show in a kind of historical break between the two that it was already thought to be connected by Struve in 52. Okay, so we know the solar system, and I would say that three main characteristics of the solar system or the planetary system around the sun is that giant planets are far away, more than 5 AU. Most of them have circular orbits or close to circular orbits, and the obliquity is very small. When I say obliquity, is the angle between the plane of the motion of the planets and the solar axis of rotation. And well, to explain this, people thought for maybe 200 years that the basic paradigm is that the planets were formed out of an accretion disk. At the beginning there was a disk, and the disk had a plane, and the plane is orthogonal to the axis of rotation of the sun, and out of this disk the planets were formed, and the idea is that in the disk there is a temperature gradient, so giant planets can be formed only at the cool part of the disk, let's say 5 AU or more. So everything was fine. Till, and yeah, this is the idea that the idea of bottom up, that at the beginning there were some planetesimals that they stick together and afterwards became planets. But the minute we went out of the solar system, then we got some problems. So here is, I plotted here up to date from the exo-planet encyclopedia, the period in days as a function of the year of discovery, only for giant planets, for planets larger than 0.1 Jupiter mass. This is updated for last week. And this is 51 Peg, the first discovery. Well, it's not the first discovery. The first discovery, which was not recognized at the time, is something that I initiated the search, which is HD 114762, but at that time wasn't recognized as a planet. Still today, it's debatable, but anyway, 51 Peg. So 51 Peg, you can see by the period, the orbital period is very short, 3 days. So this is against what people thought is one of the basics of nature, that giant planets cannot be close in. They form far away, like Jupiter, and they cannot be found close in. In fact, when we started searching at that time, people told us that you cannot find giant planets close in. I'll show you in a minute this hidden in the literature. There were questions about this. Anyway, and this is kind of a histogram of the period of the giant planets found by radiology, and you see that there are a lot of them. As you can see here, there are a lot of them with short periods. So that means that you can find giant planets nearby. So this basic feature, one of the columns of astronomy, turned out not to be true. And of course, what do you do? What a scientist do when he finds some evidence that doesn't fit his paradigm? So our image by the public is that we go to the woods and think about a different paradigm. In fact, this is not true, and in many cases in the history of science, that what happened is that scientists stick as far as they could with the old paradigm, and they try to make the paradigm more complicated. The most famous example is the epicycles, when people discovered that planets are going retrograde, so they stick still to the Aristotelian picture, but invented the epicycles. So I wonder if now scientists are stick to the idea of the basic paradigm of disk accretion and start to make it complicated. I don't know. So what people did is they invented migration. So the planets will fall far away, but they moved in by the interaction with the disk. And if you have a nice picture with nice simulation, it must be true, right? Can migration explain a highly eccentric orbit or spin-orbit misalignment, which is the obliquity? That's not clear. And at the beginning, when there was evidence only that only the giant planets are close in, but still circular, and nobody knew about the alignment, so there was not a problem. But very, very soon after the first discoveries, people found that some of the planets have very eccentric orbit, like this one. This one has an eccentricity of 0.93, which it's very hard to explain how such a planet can acquire such an eccentricity out of the disk, even with migration. Even with migration. But anyway, it turned out very soon that two basic features of the solar system are not true. When you go out, and the circular orbit are not true as well. Obliquity took much longer to find out that this is also not true in the general case. So again, obliquity is the angle between the axis of rotation of the star and the angular momentum of the orbit of the planet. And it took a while to measure obliquity, which is much more difficult than discovering planets, and also to measure eccentricity. And to help us, we discovered transiting planets, as you know, which happened that we are in 90 degrees. Our line of sight is 90 degrees to the orbit of the planet. So transit can help us by some strange coincidence or strange case, can help us measure obliquity. And the idea is the following. First of all, for transiting planets, we know that we look, our line of sight is 90 degrees to the orbital motion of the planet. But now, people use the Rossiter-McLaughlin effect. There are a few other techniques, but I will just mention this one. It's not trivial. I'll try to explain this. Suppose you have a star, and the star is rotating around its axis. So because it's rotating, this part of the star is moving towards us, so it's blue shifted. And this part of the star is moving away from us, so it's red shifted. So because of that, you will get, if you have a line in the spectrum, the line will be broadened by the rotation of the star, which is called rotational broadening. Now, suppose you have a transit. So another planet is blocking part of the stellar disk. So at the beginning of the transit, let's say that the planet moves from left to right, at the beginning of the transit, the planet will block part of the star that is blue shifted. So in the line, what we will see that the blue shifted part of the line is a little bit, there is a bump here in the spectrum. And after that, after half of the transit, it will move to cover the red part of the star, the part of the star that is receding from us. So we will get some bump here in the line. Now, usually we don't have the resolution and signal to noise to see these bumps. In fact, I don't know of any real observation of that bump. But if we measure the radial velocity of that line, even without noticing this bump, we will see a shift in the center of light of that line. So we will see a shift in the radial velocity caused by this bump. So what do we need to see the Rossiter-McLaughlin effect? What we need is to observe the star during transit and take high signal-to-noise spectrum with precise radial velocity, and the expectation is that we will see some shift relative to the velocity that we expect during that transit, and the shift will change. It will be positive at the beginning because the line will move to the right, which is positive radial velocity, and then at the middle of the transit it will be zero, and then at the end of the transit the planet is covering red, so that means that the line will be shifted to the blue. That means that we will observe shift in the radial velocity, residual of the radial velocity, which is negative. So for example, this is what we expect if the planet goes like this. So at the beginning of the transit, we will expect positive residual of the radial velocity, and then negative. So you understand that this is a very difficult observation, because you have to catch the planet transiting. The planets, they have their own agenda. They come whenever they want. So you have to be at the observatory at night and with exactly the same day, and make quick observation during the transit. The transit is 3-4 hours. So you have to make a few observations and precise enough. But if, for example, if the planet goes like this, so this is the axis of stellar axis rotation, but the planet goes like this, then you will, it's easy to understand that what you will get is something like this. The residual during the transit will be something like this and not something like this. So this is a unique way to measure the angle between the orbital motion of the planet and the axis rotation of the star. So the first one was done immediately after the first transiting planet was found at HD 209458, and indeed the radial velocity looked exactly like it was expected for alignment, for obliquity of zero of the planet. So people were very happy. And here is another one that exactly like expected. But there are some that show something completely different. For example, this one, you can see it's the other way around. So you get first negative during the transit, negative residual, and then afterwards a positive one, and that means that it is a retrograde motion. So the star is moving this way, and the planet is moving the other way. By the way, in the solar system, this is impossible to think. All the planets and almost all the moons, and the star, everything is moving in a prograde motion. But this is retrograde motion. So this caused a lot of interest in this. There's another one, even clearer than this one. So you see the angle, the lambda, which is one angle that describes the obliquity, is almost 180 degrees. So this is kind of the history, the early history of the measurement of obliquity. At the beginning, people got the obliquity zero, like in the solar system, but luckily there was one group in MIT led by Josh Wynn. Albrecht was his PhD student, Simon, and they insisted of measuring more and more obliquities, and finally, at the end, it paid off, because at the end they started to discover that systems that do not have obliquity of zero, which is a big surprise. So we lost all the three columns of our understanding of planetary system. No, the giant planets can be found very close in. Some of them have very eccentric orbit, and some of them have a high obliquity. So what do? How do you explain, especially how do you explain how within the paradigm of the accretion disk, how do you explain how planets can be found with high obliquity? So one of the leading explanations, I will show another one in a minute, is what's called planet-planet scattering, and this is plotted here. So planets are formed far away at the outer edge of the disk, but more than one. And because they come close to each other, they go through a scattering, what's called a scattering, and the scattering can push them to eccentric orbit and also can push them into high obliquity motion. And that's why we can find a high obliquity planet. So, okay, the disk paradigm has been saved. Or maybe put another epicycle, I don't know. Another idea came in a Nature paper that there is a migration, but during the migration there is another star that causes the disk to precess, and this changes the direction of the planets, so that can also induce high eccentricity. Well, if I come back to this seminal work of Albert of the measuring of the obliquity, they noticed that if you plot the obliquity as a function of the temperature of the star, there is something very interesting. That all the high obliquity, almost all of them except one or two, they all have stars with high temperature. And for the cool stars, most of them, except these two exceptions, have a low obliquity. So it seems that the high obliquity can be found only around hot stars, talking relatively speaking, and it's interesting because here at 6,000 degrees or 6,250, there is a known transition of the atmosphere of stars. Below that, stars have convective envelopes, and high, with temperature higher than that, the stars have radiative envelope. And we know that the tidal interaction is very sensitive to the width of the convective envelope, which means that those here, they potentially have tidal interaction. They can have tidal interaction with the planet, while those, they have radiative envelope, and therefore they cannot work. Tidal interaction is very... So the idea is that maybe this tidal interaction is responsible for the high obliquity. So immediately there was, in fact, in that paper, there are this three-stage scenario. I call it three-stage scenario. The planets are formed very far away. There is planet-planet interaction that scatter the planets and put them in very different inclinations, very different obliquities. And then there is the third stage of the evolution, is that there is a realignment of the planets around cool stars that caused all these planets to have very low obliquity. So at the beginning, they were formed far away, then they were scattered, and all of them were with very high inclination, very high obliquity, but then tidal interaction realigned the planets into low obliquity. Very nice. This is a theory that was discussed in the literature, and people liked it. Yeah, and this has to do with the fact that those have convective envelope. So I will leave you with this for a minute. I will come to this by the end of my talk. But just at that paper, all of those stars here have short period. They have short period, short orbital period. Why is this? Because you need transits to measure the Rossiter-McLaughlin effect, and most transiting planets have short periods. If they are far away, the probability for them to have a transit is very low. So it fits because all those, they are very near their star. So if the star has convective envelope, there is tidal interaction with the planet can work. You need two conditions for this. First, the planet has to be close. If it's far away, tidal interaction doesn't work. And second, the star has to have convective envelope. And both conditions are fulfilled for those stars here. So it's a very nice theory. Yes. No, please.
Could you explain to us why having envelopes, convective envelopes, changes whether you have or not tidal interactions? Because I don't understand it.
Yes. Well, you have to go into the theory of tidal interaction, but the idea is that in convective envelopes you have convective cells that hold the bulge. The planet creates a bulge on the envelope. And now the question is whether this bulge is following exactly the planet or it is lagging behind. And that depends how the envelope is, how the different layers of the star, how they talk to each other and how they respond to the planet. So if you have big convective cells, then this holds the envelope not to respond immediately to the position of the planet. So when the star is rotating this way and the planet is here, so there is a bulge here, but then it moves here, so the bulge lags because of that, because of the viscosity. Yeah, of course, because if the star would be circular and spherical, there is no force other than under the Kepler, except the Kepler law. So it will go in ellipse, with the constant elements. So it's only the bulge that the tides is formed. The planet forms a tide on the envelope, and that tide interacts with the planet and changes its position or its orbit. And the key issue is how fast the bulge is lagging after the position of the planet. This is it. With no viscosity, there would be a point, and there would be no interaction.
But then, should it be any relation with this obliquity and the temperature of this plot that you show there? I mean, that you have sort of clear trend, or?
Well, first of all, it's not my theory. Okay. So I'm just telling you what people thought, and yeah, maybe there is a transition here. I was thinking of this a lot, but that I understand. But the depth of the convective envelope is a very strong function of the temperature. The minute you go above 6,000 or 6,250, then the depth of the convective envelope drops. And that's it's not my theory, but no, it depends a lot on the viscosity of the envelope. For zero viscosity, there would be no tidal interaction, because for zero viscosity, the star will adjust immediately to the different position of the planet. So there would be no dissipation of energy and no transfer of angular momentum, and the planet cannot, the orbit of the planet cannot be changed. It's only the fact that the tides that the planet forms on the star that acts back on the planet and changes its orbit. They didn't explain that. It's a good question. All these are good questions. I don't know. Okay, so this is a very short introduction to obliquity, and now I want to move to and try to convince you that there is some evidence, I think interesting evidence, in the study of stellar rotation on this subject. So at the beginning, I want to just point out to a fantastic paper by Struve in in 1952, and where he really envisioned all what we have done. I'm very sorry that I didn't know about this paper when I started to work on 30 years ago. When I started to work on planets, I was ignorant enough not to know about this. But this happens many times. So what Struve wrote in this very short paper, he said like this: we have found in 52 that G-type stars, they rotate slow. That's they did they measured the V sin I, the rotational broadening of stars, and they found that in general G-type stars rotate slow. So the question is, if you think about the molecular cloud that formed a star, and you calculate what is the angular momentum that star got from the original cloud, so you have to come with the conclusion that the stars have to rotate fast. But now, he said, we found that most G stars rotate slow, and therefore, I have suggested elsewhere that the absence of rapid axial rotation in all normal solar-type stars suggests that these stars have somehow converted the angular momentum of axial rotation into angular momentum of orbital motion of planets. So he suggests that planets are a common phenomenon. That's amazing. Then he continues that how can we find this? This is in 52. So he says he considered transits and he considered radial velocity. By radial velocity, he calculates that the sun is moving in its reflex motion around because of Jupiter. It's only 12 meters per second, which was people couldn't dream about this in the 50s. But he says that a planet 10 times mass of Jupiter would be very easy to detect in an orbit of 1 day. So he was thinking of all this, and in fact, HD 114762, it's exactly 10 Jupiter masses, and the period is 80 days. So I mean, it is a visionary paper, just a very short one. I really admire the man. Anyway, so in the last few years, there is a revolution in the study of stellar rotation, because we have two satellites, Corot and Kepler, and they measured altogether 250,000 stars. And they measured the photometry, and the photometry, it's one measurement after the other without any break. And for Kepler especially, it's 170,000 stars that they measured for 4 years, almost without a break. 4 years in Kepler, it's each half an hour a measurement of 170,000 stars. It's completely different from what we had before. The goal, of course, was to find transits, but as a side effect, we have this information about the photometric modulation of stars. And we can measure radial velocity, we can measure rotation, not like Struve did by measuring the rotational broadening of the lines, but by measuring the photometry. So this is Corot, and this is Kepler, and the idea is that, if you have a star, and the star has spots, and it rotates, so what we can measure the photometry, and the photometry will be modulated with the stellar rotation. So we don't need to know anything. Just measure the photometry and find rotations. So people did it in the past, but looking back, this is a heroic effort which didn't produce much. Now, this is one paper by these guys, and you see the points model folded with the period. Barely you can see anything. This is another paper. This is another paper. But nowadays, the story is completely different. Because of that, because it's measurement after measurement without any break and very accurate and for a very, very long time. For example, this is one light curve of KOI 217. I will explain the KOI. So you see the light is fantastic. You know, every half an hour there is a measurement. So how do you handle such a gold mine of light curves in order to find the stellar rotation? There is a problem, because although the stellar rotation is constant and doesn't change, but the photometric modulation does change, because spots are coming and going, so the amplitude can change, and also the phase can change. So usually people, what they do when they have a light curve and they search for periodicity, they do a Fourier transform or power spectrum. But this is not the best way to handle stellar rotation, because the phase is changing and the amplitude is changing. And I'm preaching for this for 30 years, that this is not the best way to search for something where the period is constant, but the amplitude and the phase changes. So what do you do? I think the best approach in most cases is autocorrelation. Don't do power spectrum, but do autocorrelation. So I'll show you this one, for example. So what do you do in autocorrelation? You calculate the correlation between the data in itself when you move it. So you get the correlation between the data and itself as a function of the lag, and the lag, the peak in the lag, that gives you the period. And the autocorrelation doesn't mind if during in the middle of the light curve you change phase or you change amplitude. It's all the same for it. So here's another one which is much more difficult. Looks like noise, but when you apply the autocorrelation, so you immediately see that there is a peak there. And this peak in the autocorrelation tells you that at a lag of 4.5 days, there is the data is correlated with itself. So what we did, we applied this to all the light curves of Kepler with at the time a student, Amy McQuillan at Oxford, and Susanne Grain, and we measured the rotation of many stars. This is, for example, another one. So people are trying also wavelet. It's a very nice paper by Garcia, but I think the autocorrelation does nevertheless the same job. So this is a paper that we wrote, McQuillan, myself, and Susanne Grain, and we found more than 100,000 rotations. This is a few order of magnitude better than was done before. Other people did similar studies, but not with the autocorrelation, and found also many rotations. Well, we have to be careful what we mean rotation, because there is differential rotation. I just put here some warning, but in general it's the average rotation, or the rotation of the latitude that most of the spots are. Anyway, this I'm not going to talk about gyrochronology, but this the information about the stellar rotation is very important to people who study the angular momentum evolution of stars, because it is claimed that if you let the star live long enough, it will converge to some tight relation between mass and age and stellar rotation. And that tells us a lot about the stellar angular momentum evolution. It has to do with magnetic field and wind and everything. But I'm not going to talk about this, and I would like to move right away to what we did when we combined the stellar rotation and the planets, or the planet candidates. So you have to know that KOI in the terminology of Kepler is a star that is showing transit-like light curve and is suspected to have a planet. So we consider the KOIs as planets. So for example, here is KOI 13 that we worked about it. It's an interesting system. I'm not going to talk about this. So this is the light curve of Kepler, of the satellite, folded with the period. So you see that it's fantastic, and the depth here is very small. So this is the way Kepler finds planets. And when there is a transit-like deep, then Kepler calls it KOI. So what we did, we looked into the KOIs and we searched for rotations, and we compared the stellar rotation and the orbital period of the planet. And this is the result, again by the three of us. And what you see is something surprising, that short period planets around fast rotators are rare. So this is the stellar rotation. 50 days is long. 10 days, 5 days is the star is spinning fast. And this is the orbital period of the planet. And you can see that here there is almost no planet. So that means that short period planets, the planets that are close, that we started with, the ones that did not fit the simplistic approach of accretion, they don't like to be around fast rotators. You can explain it in a few ways. I will just mention two of them that appeared in the literature. It's very quick, just publish a paper and the next day you find two papers explaining your results. You have to be very careful about this. For example, Lanza and Shkolnik claim that, I'm not sure this is true, but anyway, I'm just mentioning this, that this is the period is some measure of the age of the planet, of the star, and therefore the young ones didn't manage yet to move into further in, which may be true or not. The other one is even more interesting, I think, but I'm not sure it's true, but that the ones that were here swallowed the planet, moved to spin up the envelope, and then moved to here because the next planet is here. Right. But what I want to finish with is this, what we did very recently, a paper that is about to be accepted, I hope tomorrow or the day after tomorrow. We still have a few things to clean the version, and I want to explain that. What we did when we measured the 100,000 rotations, we also measured the amplitude of the rotation. The amplitude of the rotation is not constant, but we took some median of the amplitudes. So we called it R. So this is the amplitude of the modulation that we found as a function of the temperature of the star of this 100,000 and 34,000. So there is for each temperature, there is a spread in the amplitudes of the stars. Some stars that rotate show large amplitude, maybe big spots, and some of them show small amplitude. But the reason for having different amplitudes could be something else, because it depends also on our line of sight. Suppose we are looking on a rotating star and we are looking from here. So we will measure high amplitude. But if we look upon the same star but from here, obviously we will measure smaller amplitude. And obviously if we will look from here, we will measure no amplitude. So the measured amplitude of the stellar rotation depends on our, of course, line of sight. So when we look here, what is the real spread of the stars here? Or what is the average amplitude? So that, of course, here, what gets into this is also our line of sight. So suppose we are looking on a sample from all different directions, then and suppose the amplitude is a function of sine I, is proportional to sine I. So roughly speaking, the amplitude that we will measure relative to the real measurement is suppressed by a factor of the average of sine I. The average of sine I is, of course, pi over 4. Now, suppose we have imaginary sample. Suppose somebody picked for us a sample of stars that we are looking only 90 degrees. Only 90 degrees. And suppose we have two samples. One sample that we look only 90 degrees, and the other one that we look in a spherically symmetric direction. So obviously, and we measure amplitudes, so the amplitude ratio of the two will be this pi over 4. But nature may be arranged for us a sample that we are looking 90 degrees to the axis of stellar rotation. And this is, of course, the KOIs. If the KOIs, if they have low inclination, the KOIs are transiting planets. So we know that we are looking 90 degrees to the axis of rotation of the planet motion. But if it is low obliquity, then the axis of the star is coinciding with the axis of rotation axis of motion of the planet. So we have this sample. So let's compare the single stars, the amplitude of the rotation, with the amplitude of rotation of the KOIs, of the stars that have planets, transiting planets. Right? So what we did, we took, we worked on this. This is the details. I skipped this, and this is what we got. This is the red points are the KOIs, and the black points are the single stars. And lo and behold, there is a difference. There is a difference in the amplitude as a function of temperature. And if you calculate the average here and the average here, the KOI have, on general, larger amplitude by 1.25. So what do you expect? You expect that the amplitude will be larger by 4 over pi. Okay, so I happen to have a calculator here. So 4 divided by pi, right? 1.27. Wow. And we didn't invent that. I mean, this came out of the data. That the KOIs have, on average, larger amplitude of rotation by a factor which is consistent with 4 over pi. Okay, I show you only, you remember the plot that I showed you, that the low obliquity or low alignment is only for the cool stars, not for the hot stars, right? So for the hot stars, if they are spread over all, we expect this effect to disappear. So, yeah, but that means that the planets probably have low amplitude. But let's move. Wow. At about 6,000 degrees, it changes. The amplitude of the KOI is lower than the amplitude of the stars. So this fits very well to the picture that has been shown. That, you know, they had the seminal work of Josh Wynne and Simon Albert. They invested a lot of time to measure the transit, the Rossiter-McLaughlin effect just in transit, and it's 10, 20 stars. We are doing this from data that we didn't invest any single photo, any extra single photon. I mean, it's all in the Kepler data. So yeah, I mean, this is I would say this is consistent with planets probably have low obliquity around cool stars. I will repeat, the KOI, the stars with planets have higher amplitude, and if the higher amplitude, that means that we are looking from angle which is close to 90 degrees. While for the other stars, obviously, I mean, it's random, so we are looking from any direction. So I'm reminding you this, and this is consistent with this, including even the transit, the transition between the low obliquity and the high obliquity. Right? So just to convince you that this is significant, I won't go into this. But we did a KS test, and these numbers, the p-value for the I'm doing this games tens of years. I don't remember I saw such numbers, you know, very, very low. It's very, very, very convincing, the fact that this here it's higher and here it's lower. Okay, I will skip. I'll skip the observation bias. We spend a lot of time thinking maybe there is some bias that caused this. I will skip this. Almost finished. So the possible summary of the talk is the following. Exoplanets can be very different from solar system. Basic accretion disk paradigm struggles with the new data, but still manages, I don't know, maybe, and that autocorrelation function, the ACF, the autocorrelation function is very effective to measure rotation, and that planets around cool stars are probably aligned, as indicated by amplitude of rotation. I could stop here, but I'm not. There is the final point. The final point is the following. We decided to take the cool stars, the KOIs, and divide them into short and long periods, because we have such a big sample of KOIs. So we took the cool KOIs and divided them into short orbital period and long orbital period. And in that sense, between the division is 5 days. Short is shorter than 5 days, longer is longer than 5 days. And now we repeated the experiment. We compared the amplitudes of the short and the long. What do we expect? We expect, because the long ones are too far away, the planets are too far away, they are not realigned. So if that three-stage scenario is correct, we expect that the long period planets are not realigned. So we expect them to be all over, and therefore that their amplitude should be as the single star. Well, this is not what happened. In fact, when we divided it, we see that the long period also have larger amplitude. Larger amplitude means that you go to this way. This is the amplitude in log, and this is the accumulated distribution. And we find that the long planets, the planets with long period, have exactly the same higher amplitude of rotation, which means if we are correct, that they are aligned as well. So our conclusion is, right, and this is very, very, very significant. So our conclusion is that this cannot work, because this can work only for short period planets. So I think that we cast some doubt on this, because we find that the amplitude of rotation of the long period planets have also high amplitude. So I'm just going to sum this up in two slides, I think. One is that to quote Thomas Huxley, that said that the great tragedy of science is the slaying of a beautiful hypothesis by an ugly fact. So maybe we did that, maybe. And the real summary is that planets around cool stars are poorly aligned from our rotation, short and long orbital period alike. And therefore, the small obliquity of cool stars probably is not by realignment. Thank you.
Okay. Thank you very much for your nice talk. So now time for some questions.
Well, it's about the amplitude of the modulation of the rotation curves have to do with the magnetic activity. So I wonder whether you have tried to infer some sort of magnetic cycle for these stars. And this is somehow connected to the view graph where you show us the amplitude versus the effective temperature, the one with the two curves, which bends over and becomes smaller for the high temperature stars without convective envelopes. So without probably magnetic cycles.
Right. So the answer is...
Okay. I mean, for instance, have you tried to measure magnetic cycles? Then I've noticed this thing. And third, you have magnetic field. So maybe you have some sort of magnetic coupling between the star and the planet.
Okay, so I'm working with a student about the magnetic cycles, in fact, very hard, and we found very, very few. But this is a work in progress. I thought a lot about magnetic cycles, in which I'm looking for changes in the amplitude. Right?
In your view graph? Could you show us the view graph with the fluctuations versus effective temperature?
Sure. If I understand correctly, it's not. But okay, let's talk about this.
Yeah, no, this one. See how the amplitude decreases.
Yeah, that's already in our first paper about reporting about the 100,000 rotation. Yeah, that is well documented, and it was done by other people as well. And so I cannot tell you why is this. This has to do with magnetic interaction or whatever. I don't know. But and I know that for hot stars, it's hard to believe that there are spots. But anyway, that's what we find. Absolutely. But I don't have a good theory for this. But what I thought you are talking about is the magnetic cycle. The magnetic cycle, as far as I understand it, is that there is a modulation of the rotation for a specific star, like the 11 years of the sun. So we don't have data enough for 11 years. We have only 4 years in Kepler. But what I hoped that some stars would have shorter magnetic cycle. It means that you see some modulation, and then you do something like that, and then again. And we do find few, very few. We are looking for this right now, as we speak. But that's something else. This is not what is measured here. Here is measured the average or the median modulation over the 4 years.
The other thing has to happen too. This is very suggestive that the modulation should happen too. And probably you don't have the baseline, enough baseline, because the cycles are longer than this 4 years.
Probably true. Yes. I agree. I'm aching of that. We are working with this a lot.
Hi. Thank you.
this great talk. You made quite a strong point that autocorrelation is a better method to measure and to detect this kind of periodicities, right?
Better than the regular
Fourier transforms
in many cases.
Yeah.
In fact,
but let me finish the question, if I may. So in the autocorrelation function that you showed, there were also there were several peaks.
right.
So, which I expect you would see the same in a Fourier transform or Lomb-Stargell periodogram of those time series, right? So the question is, how do you decide which of the photometric periods you trust as rotational periods? That was the first question. The second is on the sample of the results, these results that you've shown, these latest results. So from either from someone who is not in the exoplanets field, I'm wondering what of the KOIs, and I'm wondering if the mic stands, what fraction of the Kepler objects of interest are actual planetary systems, if we have a figure for that.
Okay, so first about the autocorrelation, we spent more than a year of work in order to form a procedure, what peaks we trust in the autocorrelation or not. I think we have now a good way to do it. There are borderline cases. I'm not hiding this. So the 993 that we have in this sample are only the ones that we are absolutely sure that we think that they are real rotation. So there is a problem, but there is also a problem in power spectrum as well. What I'm claiming is the following: that in some cases, not all cases, and I have many examples of this, that the peak in the power spectrum will be buried in the noise because of the fact that the amplitude is not constant and because of the phase change. While the autocorrelation does mine, and the autocorrelation peak will be above the noise. I mean, for easy cases, you get the same result for both techniques. And also, by the way, the autocorrelation, the power spectrum, in many cases, finds half of the period, which is not true. And in the autocorrelation, you see that immediately. So, you see, I mean, you have a data, and you have a model, and you have an algorithm. The model is that the star is rotating, and there are spots on it. And you know that the amplitude changes, the phases change. Now you have to choose your algorithm which best fits your model. Or power spectrum is to find sine functions. Sine functions, that's what I learned, maybe it has been changed since, but that was a long time ago, have the same phase and the same amplitude all over. So why apply an algorithm that is not matching your physical or astrophysical model? This is always the question that I am asking myself when I choose an algorithm to analyze data. The data is, I believe, the model is that there is a change in the amplitude and there is a change in the phase. For easy cases, when you can see in the data itself the amplitude, that's everybody can do that, even a child at the second grade. We are talking about something that the modulation is buried in the noise. But because it appears so many frequencies, so many periods, then your technique should pick this up. But if your model is that this signal, which is buried in the noise, is not with a constant phase and not with constant amplitude, why apply power spectrum? This, in my eyes, I mean, it's so obvious. Really, I'm preaching this for 30 years, but the problem is that people are used to do power spectrum. And And because for photometry it was unevenly spaced data. For unevenly spaced data, people didn't know how to do autocorrelation. I know, but that's a different issue. But now it's almost evenly spaced data, so why not apply the right thing? That's my feeling. I really don't understand why people are sticking to power spectrum. Okay, power spectrum is very easy, you know. With FFT, I mean, it doesn't cost you much CPU. That's my preaching line. About the frequency of KOIs. This is a big debate between the Americans and the Europeans. The Americans, Kepler is there, they claim that the false alarm frequency is a few percent. It depends to what threshold, it's a complicated issue, but a few percent. There are a few papers published by the Europeans that claim that the false alarm is something like 10% or maybe 20%. So this is an open debate.
Okay, yes, one very simple question.
Well, this is more a comment. When you try to explain how the raster McLaughlin effect works, you say that you show this bump moving on the spectral line. You
Right.
say that there is no case, when the real bump was observed. There are indeed some cases.
Sorry, I didn't understand the last sentence.
You say that there are no cases where the real bump on the moving on the spectral line was observed.
Yeah, as far as I'm aware, yes.
My comment is that there are some.
Okay, thank you.
Two, just was 53. This is.
Really? Okay.
Andrew Cameron, and also one by Davide Condolfi on Coro 11. Just.
Okay, thank you. That's very important. I mean, to see the real bumps.
There are two fast rotators. Of course.
Yeah, right. Yeah, they are fast
I
rotators.
tend to do fast
Okay,
rotators.
thank you, yeah.
And then I have a question on just this plot.
On this one?
You can try to simulate a sample where the stellar orientation is just random. I'm not sure that if you try to do that, you get this kind of distribution, which is more or less symmetric around the average. Did you try to do that?
No, we did not. We tried many other things. We were thinking of this. And in fact, this is something that we plan to do in the future, but we did not do it right now. But the question is, we don't know, which would be very, very interesting. We don't know what is the real distribution. No, for the KOIs, no. For the KOIs, if this is the line, this is the real distribution. The single stars we don't know because it's a cumulative process. We can. No, we did not do that. We tried a little bit, but we played a little bit, but we didn't go.
I mean, I'm thinking that the black point looks more or less symmetric around the average. I would expect something cute if you have a random distribution of information.
Could be. I don't know. Yeah.
Okay, so we are going to stop here. Just to remember that now we have the scientific coffee in the library. Okay, let's thank again Tsevi for his talk.